Today, class, in lesson 4.1, we're going to be reviewing all the fundamental basics of a polynomial function. So a polynomial function is defined by the form of f of x equals, we have a sub n times x to the nth power, and then a sub n minus 1, x to the n minus 1 power, and etc., etc. The key to this function is understanding that the a sub n, so these coefficients, must be real numbers, and the the n value, specifically the n value in those exponents, has to be a positive integer. The domain of a polynomial function is the set of all real numbers. So the first thing we want to look at is, in these examples of possible polynomial functions, is this a polynomial function? If so, then I want you to state the degree of the function, and if it's not, then we're going to need an explanation for why it is not a polynomial function. Keep in mind, when we mention the degree of a function, the degree refers to the highest, well, right off to the side, the highest exponent in the function. So as we look at this first one, we have 3 times x to the 1/3 power minus 5. This one is not a polynomial function because that exponent of 1/3 is not a positive integer. Remember that 1/3 has to be a positive integer. The other reason why you could look at it as not being a polynomial function is if you remember what n to the, or x to the 1/3 means, that actually means 3 times the cubed root of x minus 5. So in reality, this function is a cubed root function, not a polynomial function. If we look at the second example, we have 2, in example B, 2x to the -3rd plus 3x minus 8. Well, once again, this one is not a polynomial function because that exponent of -3 is not a positive integer. And again, if you really understand the real meaning of this function, that negative exponent essentially becomes a fraction 2 over x cubed plus 3x minus 8, which means this function is actually a rational function, which we'll be learning about later in this chapter. If we look at the third example, C, this one is a polynomial function. Our coefficient is a real number, -5. Now, some of you may look for the variable and realize that the x is not present. That's because it's the same as having x to the 0 power. As we know, x to the 0 power is the same as 1, so -5 times 1 is just going to be -5. Because the exponent is a positive integer and the coefficient is a real number, this is a polynomial function. And the degree of this polynomial function is a degree of 0. Remember, it's the highest exponent, and in this case, the exponent is 0. This is what we call a constant function when the degree is 0. In our third example, we have 3s times the quantity of 2s squared minus 1. But when we're looking at this one, we do need to understand that the equation is not currently in what we would call standard form. So the first thing we need to do is to distribute that 3s. That would give us 6s to the 3rd minus 3s. This function is a polynomial function. Once again, my coefficients are real numbers and my exponents are positive integers. And the degree of this function is 3 because the highest exponent is that 3. That would mean this one is what we would call a cubic function. Okay, as we look at the next two examples, E and F, I would like you to try to answer the questions. Is this a polynomial function? And if so, what is the degree of the function? Now, as we look further down at some of these other examples, these are what some polynomial functions might look like. Now, one thing I want to point out is the direction of the graphs. So we might see some polynomial functions that are both kind of pointing in the same direction. We call this the end behavior, and we'll be reviewing that momentarily. And we have some where they might be pointing in opposite directions, like this one. Okay, in these polynomial functions, you'll notice that there could be a variety of different kinds of turning points. This one has a corner, kind of a cusp. There's a hole in the graph. This one is not an example of a polynomial function, and that's because we need to remember that the domain of a polynomial function needs to be all real numbers. Well, because of these gaps and these holes in the graph, we do not have we do not have a domain of all real numbers. This first one is a polynomial function because it is continuous. There are no gaps in the graph. Another quick review about some of the terminology. You'll notice that this polynomial function has a variety of x-intercepts. Well, we kind of refer to those x-intercepts in a couple of different ways. These first two x-intercepts, you'll notice that the graph is actually crossing through the x-axis. So we say that these cross the x-axis at these points. You'll notice that this x-intercept touches the x-axis right here, and then it kind of bounces right back down again. So we say that this one bounces off the x-axis. And then again, we have another x-intercept here that will cross the x-axis. It starts at the bottom and it crosses through to the top. So when we're plotting our points, we're going to be talking about whether or not our function is going to cross or bounce at those x-intercepts. Okay, getting back to some basic definitions. We mentioned before that the degree of a polynomial function refers to the largest power of x, and that it must be in standard form. So we saw one example where we had to multiply it out to get it into standard form. Turning points refer to the points where the function changes from increasing to decreasing, or vice versa. So basically, a turning point is any point where it's going to change directions. If a polynomial function of degree n, or if we have a polynomial function with degree n, then the function has at most n minus 1 turning points. So if our function, for example, is a x to the 4th function. Let's say we have x to the 4th, x to the 3rd, x to the 2nd, etc. And the degree of this function is 4. Then the most number of turning points, or the most times it could possibly turn, would be 3. Now it could turn less than that. It could have only 2 turning points, or even 1, but at most it's going to have 3. Okay, let's talk about the real zeros. Now remember, the real zeros we refer to as x-intercepts. So for example, the point r comma 0 is actually an x-intercept of the graph. R is what we call the real zero of a function. If we were to take that r value and write it as x minus r, this is going to be a linear factor of the function f of x. And then finally, if we set the function equal to 0 in order to solve for the r value, what we're finding here is a solution, also known as a root of the function. Okay, then let's talk about multiplicity. Multiplicity refers to, and I'm going to switch colors here, multiplicity refers to the power of the binomial in factored form. Okay, and I'm going to give you some examples of that. But for example, if we had x minus r, so again, that's that factored form, to the m power. The m, that exponent, refers to the multiplicity. So we look at the multiplicity two ways. If that m value is odd, so if we have an odd exponent, that means that the graph is going to cross the x-axis. Oops, sorry, I wanted to erase that. Okay, it's going to cross the x-axis at that point of intersection. If the multiplicity is even, that's when the graph is going to bounce off the x-axis, as we saw in the previous example. Okay, the last thing then I want to review a standard form versus factored form. So factored form is when we're seeing the polynomial function written in this x minus r form. And we could have something like this, x minus 2 squared, so we could have that binomial with an exponent, times x minus 1, for example. This would be factored form. Oftentimes, we ask that you write that function from factored form into standard form. If I'm writing in standard form, I'm going to have to multiply this out. And that's where you have to be comfortable with raising binomials to different powers, using FOIL or other versions of distributive property to multiply those out. So if I was to multiply this out, x minus 2 squared, for example, that would be x squared minus 4x plus 4. Then I'd have to multiply that trinomial times the x plus 1. And when I put all that together, let's see, x cubed plus x squared, I'm going to have a negative 4x squared and a negative 4x. I'm going to have a positive 4x, and I'm going to end with a positive 4. So if I combine all of my like terms, my factored form will be x cubed. Let's see, we're going to have minus 3x squared plus 0x and plus 4. So there would be my standard form from my factored form. And that's the first thing that we want to get into. How would we write a polynomial function in standard form if we are given the following pieces of information? So to start with, I'm telling you what the zeros are, as well as the multiplicity of those zeros. I'm also giving you information about the degree of the polynomial. So again, that's going to be the highest exponent. Now remember that the zeros of the function, so if I'm giving you, this goes right back up to all of this that we were saying up here. If the zeros of the function are, let's say, 1, then that means that x minus 1 is a linear factor. So what we can do is take each of these zeros, like 1, and we're going to write it as a linear factor x minus 1. Now we have a second zero of negative 2. If we write that as x minus negative 2, that's going to become x plus 2. Now this x plus 2 has a multiplicity of 2. That means that it has an exponent of 2. So my factored form of this equation is x minus 1 times x plus 2 squared. I need to rewrite it in standard form, which is what we just reviewed a second ago. So in standard form, if I was to multiply this out, okay, x minus 1, first I'm going to square the binomial because order of operations, we do exponents first. So x squared plus 4x plus 4. Then I'm going to multiply the binomial by the trinomial. You'll notice the technique that I used up above was that as I multiply these terms, I tend to line up the like terms so that it's easier to add them together afterwards. So when I start multiplying these, x times x squared is x cubed, x times 4x is 4x squared, and x times 4 is 4x. Negative 1 times x squared is negative 1x squared. You'll notice I'm lining it up with the other x squared. Negative 1 times 4x is negative 4x, and negative 1 times 4 is negative 4. And now if I want to add these together, I've got x cubed plus 3x squared minus, plus 0x, and minus 4. So my function in standard form is this. Notice that we were also told that the degree of the polynomial was to be 3, and we have ended with a degree of 3 in our final standard form. Now I want to talk a little bit, class, about this end behavior of a graph. Keep in mind, end behavior refers to basically the direction that the graph is going to be pointing as the x values approach positive infinity and as the x values approach negative infinity. So we're basically saying as the graph moves toward the right, what will happen to the y values, and as the graph moves toward the left, what will happen to the y values. Our end behavior can be one of 4 things. First, our end behavior can be pointing in the same direction. The way to determine if the end behavior is going to be pointing in the same direction is to look at the degree of the function. If the degree is even, then that's how we know that it's going to be pointing in the same direction. Okay, the other possibility is that we could have end behavior pointing in opposite directions. In this case, we're looking at the degree being odd. This is going to end up being opposite directions. Then we have to determine whether the end behavior is going to be pointing up or pointing down. That's when we start looking at the leading coefficient. If the leading coefficient is positive, then the graph is going to be pointing up. If the leading coefficient is negative, the graph is going to be pointing down. Now, when the graph is pointing in opposite directions, we're obviously going to have one up and one down. That's when I usually try to remind people about slope, okay? A function, a linear function, for example, 2x plus 1, this linear function does have an odd degree, and therefore it is pointing in those opposite directions. So think about the slope. If the leading coefficient is positive, then the graph is starting in the lower left corner and moving to the upper right corner. If the degree is negative, then it is moving in the opposite direction. So when we're looking at these end behaviors, this one would have a leading coefficient that is positive, just like the positive slope. This one would have a leading coefficient that is negative, like a negative slope. So now let's take a minute and examine a couple of functions and look at their putting some of this information together. So for example, in example 3 here, we have a polynomial function that is currently in factored form because we can see that it is written using these linear binomials. We want to determine the degree. When determining the degree, we do have to pay attention to what the standard form would look like. So if we were to multiply this first term to the third power, and then multiply it by the first term in the second binomial to the fourth power, we would end up with an x to the 7th power as our first, our leading term in our expression. Therefore, this one has a degree of 7, which means this is an odd function. Remember that odd functions are going to be going in opposite directions. Okay, maximum turning points. Remember that the maximum turning points is always 1 less than the degree. So that means the maximum turning points here are 6. It can change directions at most 6 times. In terms of the real zeros and the multiplicity, remember that each one of these factors is going to produce a real zero. So we have a factor of x plus 4 and we have a factor of x minus 2. The real zero of this one, if I set this equal to 0 and solve, my first 0 or x-intercept is negative 4. If I set the second factor equal to 0 and solve, my second x-intercept is 2. So this one has 2 real zeros. However, the next thing we need to look at is the multiplicity. This first one has a multiplicity of 3. Which means that at negative 4, since this is an odd multiplicity, we will cross the x-intercept at this point. The second one, x equals 2, has a multiplicity of 4. And because that's an even multiplicity, this one will bounce off of that point on the x-axis. Okay, finally, let's talk about the end behavior. We already knew that the end behavior was going to be pointing in opposite directions because our degree was 7. It was an odd degree. Now we need to look at the leading coefficient. And again, if you go back to the original expression, and when you multiply x cubed times x to the 4th, you will be getting 1x to the 7th. Because that leading coefficient is positive, a positive 1, that means our end behavior, just like a positive slope, is going to start in the lower left-hand corner, and it's going to end in the upper right-hand corner. When we're describing this, then we would say that as our graph approaches negative infinity, so as we move to the left, our y values are going to be going down or approaching negative infinity. As we move to positive infinity, in other words, as our x values move to the right, our y values will move up, in other words, toward positive infinity as well. So here would be our N behavior. If we look at example 4, okay, once again, first thing we want to do is figure out the degree. So think of it in terms of if you multiplied this out in standard form, you'd be multiplying x cubed times x squared times another x. Well, if I multiply all of those together, I'm going to end up with a leading coefficient or a leading term of negative x to the 6th power, which means my degree is 6. It is even, and this graph is going to be pointing in the same direction. Okay, the maximum number of turning points, again, is always one less than the degree. So in this case, the most that this graph can turn is 5 times. Zeros. Again, if we take each one of these linear factors, starting with this negative x cubed, that's going to give us one of the zeros. X minus 3, that's going to give us another one. And x plus 2, that's going to give us a third zero. If we set each of these equal to 0 and solve, we're going to get an x-intercept of 0, an x-intercept of 3, and an x-intercept of negative 2. In terms of multiplicity, our x-intercept of 0 is going to have a multiplicity of 3 because it was cubed. Because that's odd, this one is going to cross at that point. The x-intercept of 3 has a multiplicity of 2. Since that is even, we are going to bounce off of that point. And our third one has a multiplicity of 1, x plus 2 to the 1st power. Since that multiplicity of 1 is again odd, we are once again going to cross at this point. Now, and back to the N behavior. Since we had already determined that this was an even degree, we know that this graph is pointing in the same direction. Since the leading coefficient, though, was negative, look back at that negative x to the 6th, that means that this graph has N behavior pointing in the downward direction. So, as our x values approach negative infinity, our y values will also approach negative infinity. As our x values approach positive infinity, our y values will also approach negative infinity again. And example 5, we're going to look at together as a class when we come back in. Okay, the last thing I want to do is look at example 4, and we want to look at putting all of this critical information together to sketch a graph of the function. So remember that this is the same example from up in our chart. Some things that we know. We already knew that the N behavior was pointing in the same direction and both pointing down. We knew we had x-intercepts at 0. We had another one at 3 and another one at negative 2. In terms of the x-intercepts, we knew that at 0, we were going to cross through this point. At negative 2, we were going to cross through this point, and at 3, we were going to bounce off of this point. Now, a third piece of an additional piece of information that may be helpful is to find the y-intercept. Okay, if you look, some of you are going to recognize that we already have the y-intercept on the graph since we already have the origin, but how would you find a y-intercept if this wasn't the case? Remember, to find a y-intercept, all you're doing is plugging in 0 for x. So negative 0 cubed times 0 minus 3 squared times 0 plus 2. Well, regardless of what I get here and here, as soon as I multiply by 0, this entire y-intercept becomes 0 as well. So with what we have to sketch, we know that our graph is going to start in this lower left corner. It's going to come up and cross through this first x-intercept. At some point, it's going to turn directions and cross through the next x-intercept. At some point, it will turn again, and it will bounce off this one, and it will continue down to that lower right-hand corner this time. I'm going to erase that little arrow here that I didn't need. And this is a brief sketch of our graph. What I would like you guys to do is to graph this function now. We've got an idea of what it looks like. We're now going to graph this function on our calculator using a domain of negative 2.5 to 4. So that means that our x-min is going to be negative 2.25. Our x-max will be 4, and you can decide what your scale is going to be. I would suggest maybe just 1. Remember, do not bother putting in the y's. Instead, I want you to go to zoom, fit and fit the graph to this domain. Once you're there, I would like you guys to determine what are the actual turning points in this graph. We can visually see that there are two turning points, this one here and this one here. I would like to know what those ordered pairs are, because then using those ordered pairs, we can start to determine where does this graph, on what intervals does this graph increase, and on what intervals does this graph decrease. And when we come into class tomorrow, we will talk about that.